Hello students, welcome back to your favorite and India's most affordable learning platform, Physics Wala. So in today's session, we are going to start the first class of Nexus Physics class. So in that, we are going to start with the first chapter, that is units and dimensions. So before going into the lecture, so as this is my first class in this batch, so let me tell you how to utilize this batch. So you have completed 10th recently and entered the class 11th. So now how you proceed to get the maximum score in JEE or NEET, whatever you are preparing for. So and how this batch is going to help you guys. See, in the next 2.5 months to 3 months, I am going to cover the complete syllabus of class 11th. Okay, so that too, the topic wise sessions will be taken, not as a one shot. So it's a topic wise session. So now I am taking units and dimensions. It's a first lecture. So I'll take 2 more lectures in units and dimensions. So where you get complete concepts of the lecture. So and in between the sessions, not only the concepts, so I am going to solve so very large number of numericals. So that includes previous year JEE questions and previous year NEET questions. Okay. So what you guys have to do is, so just follow the lectures daily and make a short notes. That's very, very important. So making short notes is very important. So if I'm spending 1 hour or 1.5 hours on this class, so just spend more 10 minutes, sit like that and just write the summary, whatever you have learned in today's class. So that's very, very important. So once you understood the lecture and wrote the short notes, and while proceeding for the next lecture on the next day, you just recap the previous lectures. Okay, na? So this is a best method you can retain the concepts. Okay, na? So otherwise you'll forget after some days. Okay, so that mistake has been done by many of the students till now. Okay, so don't do that mistake from the starting itself. I am saying, so just follow the lectures properly, write the short notes and daily revise it. Okay, chalo. So hope you guys will follow this. So myself Krishna, I am your physics faculty guys. So today I am going to start the first session of units and dimensions. So in today's session, I'll start with just dimensional analysis, how to write the dimensions of different physical quantities. So this chapter, actually very easy one, but some formulas will be from different chapters. The formulas, whatever we are going to write dimension analysis, so they will be from different chapters. So most of the formulas you have studied in class 9th and class 10th, the basic formulas. So like electric current, electric field, potential, so such speed, velocity, acceleration, force, work, energy. So these physical quantities you already studied. But so some of the quantities, so you'll come across newly in today's session. So what you do is you just remember the formula and see how I'm applying the dimension analysis. That's very important because some formulas are very new to you. So in this class will be very new to you. That's for sure. Because this units and dimensions includes all the chapters. Okay. So you just remember the formulas. And again, whenever that chapter comes, I'll explain again how that formula has come and what is the derivation behind that. So everything I'll explain at that time in that chapter. So as of now, I'll just give the formula and then dimension analysis for that. Clear guys? Chalo. So be with me for the next 1 hour so that you can gain the maximum concepts. So whatever the disturbances are around you, just keep them away. Okay? Chalo. Let's start with the session. So first, today's targets are physical quantity. What are first physical quantities? So and then how do we write the dimensions and the dimensions of the derived physical quantities? So these are our basic 3 targets. Okay, chalo. So first thing, what are physical quantities? So the physical quantities, you have learned many physical quantities in physics till now, right? So length is a physical quantity, work, force, everything is a physical quantity, whatever you learned in the physics. So the quantities which can be measured by an instrument by means of which we describe the laws of physical world. So the physical quantity, so which consists of a numerical value and it consists of the unit as well. It consists of a physical value, so which is numerical value, and it will have the unit as well. So the numerical value is a 1, number of times a unit occurs, whereas unit is a comparison. So just this is a basic definition. We do not have anything to do with that. Okay. So just let's proceed further. So this is important. So there are 3 types of physical quantities we have. So one is the fundamental physical quantities, then derived physical quantities, then supplementary physical quantities. So these are the 3 major types of physical quantities. So these fundamental physical quantities which do not depend on the other. Okay, na? So these are independent of any other physical quantity. Okay, na? They are fundamental, means they do not depend on anyone. So whereas, so the derived physical quantities are the ones which are derived from the fundamental. So 2 fundamental quantities, physical quantities, are more than 2 fundamental physical quantities combined to form the derived physical quantities. Okay, and supplementary physical quantities are separate. That's the third part. Okay, now. So now let's move further. So the fundamental physical quantities, as I'm talking about here, so which does not depend on any other physical quantity. They are independent. So we have total 7 fundamental physical quantities. Everyone should learn these 7 fundamental physical quantities. So which includes length, mass, time, temperature, current, luminous intensity, and amount of substance. So and there, what are their SI units and what are the symbols? You know that length is measured in meters. So the symbol we use meter, and mass is measured in kgs, kilogram. So which we use kg. And time we measured in second, so which we use second. And then temperature, Kelvin, so K. And then electric current, ampere, so A. And luminous intensity, we use it very rarely, so you can just mark it. Okay, na? So we use it very rarely. So candela is a SI unit, and CD we denote it with. And amount of some substance which we measure, SI unit is mole, and the symbol is MOL. Right? So this part is clear for everyone. So no doubts, you have to remember these 7 physical quantities, fundamental physical quantity. So quantities, just come with me, just say with me. So length, mass, time, temperature, amount of substance, electric current, and luminous intensity. So these are the 7 physical quantities which you should remember. Okay, na? So from these physical quantities, so we get the derived physical quantities, so which are made up of fundamental physical quantities. So for example, if I talk about the area, so area is nothing but the length into length, right? So if I take the square, it's side into side. So if I take the rectangle, it's a length into breadth. So something length into length or length into breadth. So length is measured in meters and breadth is measured in meters. So meter square. So this is one fundamental physical quantity, and this is also one fundamental physical quantity. So these two combined, and we have the derived physical quantity called area. And similarly, volume also, length into breadth into height. So length is one physical quantity, breadth is again, breadth means which is measured in meters only again. So length is measured in meters. So this is also measured in meters. So this combinedly, these three are 3 physical basic fundamental physical quantities, so are combined to form a derived physical quantity called volume. Done? Understood this part, guys? Chalo. So next. So and velocity is one more derived physical quantity. So velocity you already know. So distance by time or displacement by time, which is meter per second. So then, so acceleration, so the change in velocity by time. So change in velocity, which is meter per second by second, which is meter per second square, or meter second to the power minus 2. So and then charge we have, you know that. So current is equals to Q by T. You learnt it in your 10th grade, right? So from there, charge formula, what you can write? The charge is equals to current into time. So current, electric current is one fundamental physical quantity. Time is another fundamental physical quantity. These two combined to form the another derived physical quantity. Clear? Understood? Chalo. So similarly, you can write it for the temperature gradient. So what is temperature gradient? So the change in temperature per length. Change in temperature per length, which is change in temperature is Kelvin. So length meter. So these two combinedly formed the other derived physical quantity called temperature gradient. Okay. So like that, we are going to write the dimensions for different physical quantities, whatever you learned till now. So for all those physical quantities, we are going to write the dimensions. So very, very important how to write the dimensions. And many times the questions were asked in the NEET as well as JEE. One question comes for sure in NEET and JEE based on this concept. Okay, so let's go further. So now, so as I said earlier, we have one more type of physical quantities. So what's that? Supplementary physical quantities. So fundamental we have seen, derived physical quantities we have seen, and then supplementary physical quantities. So there are two types of supplementary physical quantities. One is a plane angle, the other one is a solid angle. So what is plane angle? The theta is equals to arc by radius. So this is the arc distance and this is the radius. So theta is equals to arc by radians. So which is nothing but L by R we write, right? So you learned it in your basic maths, this one. Theta is equals to L by R. So the unit is radian. So whereas here 360 degrees is equals to 2 pi radian, we know that. And pi is nothing but 180 radian. Sorry. 180 degrees is nothing but pi radian. 180 degrees is a pi radian. These basics you already know, right? So what is solid angle? The solid angle is for the solid objects. For example, the 3D version cone if you take, so then the angle, let's suppose this is the 3D version cone. So the angle made by the cone at the bottom, so in 3D, that's a solid angle. Clear? Understood, guys? So these are the two supplementary physical quantities. So basically they do not ask questions based on this. So we have to derive the dimensions for these physical quantities, derived physical quantities. This is very, very important. Okay, na? So chalo. So how do we derive the dimensions now? So since there can be different system of units, we can specific symbols for fundamental physical quantities. So for example, if I take the length, so I can measure it in meters, centimeters, millimeters, nanometers, angstroms, so micrometers. So like that we have many number of units. Inches are there, feet are there. So to standardize that, so what we are using is the dimensions. One single symbol we are going to use it. Okay. So for length, for example, if I take, this is a fundamental quantity. So the length can be measured in meters, centimeter, feet, inches, and etc. So from now onwards, for length, we are going to use L, the dimension. So for length, it's going to be L. So if I take the mass, I'm going to use kg, right? So M. If I take mass is measured, mass can be measured in kg, grams. So like that, many units will be there, right? So for that, we are going to use M. So and so on, etc. So that I am going to represent it in the next slide. So see here. So as I said earlier, for the all fundamental physical quantities, we are using the standardized dimensions from now onwards. So the whenever the length comes, so the dimension L we use, and mass M we use, and time T we use. Okay, temperature K. So temperature, sometimes they also use theta. Okay na? So in some reference books or in questions, they might mention theta also. Okay, chalo. So in electric current we use A, and luminous intensity we use C, and amount of substance we use mole. Okay, chalo. So the dimensions are the powers to which the fundamental units are raised in order to express the derived unit of the physical quantity. So for example, if I say, what are the dimensions of length? So the length dimensions means don't write just L. L is not the dimension. So their powers means C. So here the length, so there is no M in the length, M to the power 0, where L will be there, L to the power 1, and then T to the power 0, T to the power 0. So these are the dimensions of length. So like that we write. So similarly mass, M to the power minus 1. So L0, T0. So even if we don't represent these, no issue. L to the power 0, T to the power 0, we may mention it or may not mention it. So that doesn't matter. Clear? So like this, we are going to write the dimensions for all the derived physical quantities now one by one. Almost some 50 formulas, 50 physical quantities I am going to take from now onwards, and I'll write all the dimensions for one by one. Okay. So what you guys have to do is just follow it, and some formulas will be new for you. Just learn the formula and understand how I wrote the dimensional formula for that. Clear? So from now onwards, it's very, very important. From this line onwards, it's going to be very, very important. Whatever you have seen now till now, it's just the basics. Okay. Chalo. So now let's go for one by one. So let's write with me. So first of all, so what are the dimensions for area? So area means basically we write meter square are the units, right? Like this. Meter square are the units, are the length into length or length into breadth. So which we write it as. So the dimensions for the meter square. So what meter square means length. So length means L to the power 2. Shall I write? Yes or no? So these are the dimensions for area. So similarly, volume. So which we write it meter cube, or so directly write it as, so the L cube, length into breadth into height, L cube, right? Similarly, so what is the units of speed or velocity? So speed or velocity is nothing but, so the distance by time. Write along with me. Just you can see all these, right? Just pause the video and write the formulas for everything. So the distance, which we measure it as L, the distance is nothing but length. So now the time is T. So the dimensional formula will become L T. So L to the power 1, T to the power 1. If I write L T means L to the power 1, T to the power minus 1. If it goes up, it comes out to be minus 1 kada. So T to the power minus 1. Clear? Chal. So momentum. So what's the momentum formula you learned in grade 9th? So the linear momentum is equals to mass into velocity. You have seen that mass is m, and then velocity is L. Just now here, right, he wrote. So ml t to the power minus 1. So which is nothing but ml t to the power minus 1 is a dimensional formula for momentum. Mass into velocity. So similarly, acceleration. So acceleration is meter per second square are the units. Meter per second square. Yes or no? So or else you just write like this. So the velocity by time, the change in velocity by time. So you know the velocity formula. What is velocity? Just now we wrote L t to the power minus 1 by the time is again t. So which comes out to be L into t to the power minus 2. L t to the power minus 2. Next. So what is force? Force formula you already know, right? So mass into acceleration. Mass, for mass we have m. Yes or no? For mass we have m, and then so for acceleration just now we got L t to the power minus 2. So the dimensional formula for the force, which is equals to ml t to the power minus 2. So very, very important. You should remember this one. You should remember this. So I am making it star. Okay now? Clear? So and then what is the work formula? Work done. So work done is equals to force into displacement. Work done is, you learned it in grade 9th, this one also. Work done is equals to force into displacement. So force formula we already know, ml t to the power minus 2. So into displacement. So displacement means length. So which comes out to be m l into l, l square into t to the power minus 2. So this is a dimensional formula of work. And similarly, right, for the energy, you learned in the grade 9th that work energy theorem. For work energy theorem, so you know that the work done will be equals to energy supplied. So therefore the work and energy will have the same dimensions. Whatever the work dimensions are there, so will be there for the energy also, ml square t to the power minus 2. So from this slide you should remember, compulsory you should remember the dimensions of the force. Okay, write along with me the dimensions of the force, m l t to the power minus 2. Because to derive the other physical quantities, so we should know this. Okay, so the force is ml t to the power minus 2, and whether it is energy or heat or work, so the work or energy, so the dimensions, this also you should remember. which is ml square t to the power minus 2. So this is ml square t to the power minus 2. So you should remember. Here if I talk about the energy, so any kind of energy it can be. It can be any kind of energy if they mention. So it can be gravitational potential energy, or it can be just potential energy, or it can be heat energy, or it can be kinetic energy. So all the kind of energies, whatever the energy, wherever the energy is mentioned, you just use the dimensional formula of energy as ml square t to the power minus 2. That's it. So the energy means here it can be the potential energy, which is U, or it can be the kinetic energy, which is denoted by K, or it can be heat, which is H or Q. Sometimes it can be denoted with H or Q. Heat is also a form of energy, right? You already learned in the grade 9th, whatever the grade 10th. So whatever the energy supplied will be equals to the work done, and which will be equals to the heat released, right? So the same thing here also. For all of these, the dimensions are simply energy dimensions. Clear this part? No doubts in the first slides of the dimensions of derived physical quantities. So just let me know if you have any doubts, guys. Chalo. So let's move further. So let's increase one level up. See here. So again, the kinetic energy and potential energy I am talking about. So which will have the same formula. So same dimensions, m l square t to the power minus 2. So whatever the energy it can be, so the dimensions are going to be same. So and then torque is a new term to you. So just let me write the formula. Torque, we get it in the rotational motion chapter. So where the torque formula is tau, which is equals to, it is denoted with tau. So it is force into the perpendicular distance. The formula is force into perpendicular distance. So now you know the dimensional formula for force. What is that? ml t to the power minus 2 into, and perpendicular distance. Distance is nothing but length. So which is equals to, shall I write m l square t to the power minus 2? Shall I write m l square t to the power minus 2? So that means what you can say here, the torque, energy and work, so they all have the same dimensions. So write down here. So just note that point. So the torque and the energy and then the work done, so they all have the same dimensions, m l square t to the power minus 2. Done? Chalo. So and power formula also you know in grade 9th and in grade 10th. So it's a work done by time. So now you know the dimensional formula of work done. What is that? m l square t to the power minus 2 by, so time capital T. So if it goes up, it becomes m l square t to the power minus 3, m l square t to the power minus 3. Clear this part? Chalo. So this is the dimensional formula. So always represent the dimensional formula in the square brackets like this. Done? Chalo. So the impulse. So impulse is nothing but the force into time. So this term also might be new, but CBSE students, you already learned in the grade 9th, but formula you know you did not learn, I guess. So force into time. So which is nothing but, so force formula you already know. What is the force? ml t to the power minus 2 into, so then time. So time t. So which is equals to ml t to the power minus 1. ml t to the power minus 1. Clear? Chal. So see, and you can also remember one thing, that the impulse is equals to change in momentum. The impulse is equals to the change in momentum. In questions, they might ask which of the following two physical quantities will have the same dimensional formula. Which of the two can have the same dimensional formula? So if you observe here, impulse has ml t to the power minus 1. And also see the linear momentum, or linear momentum, ml t to the power minus 1. So here also ml t to the power minus 1. So the impulse is equals to change in momentum. I is equals to delta p. So remember this also. Done? Clear. Next. So and we have mass density. What does it mean by mass density? So mass per unit volume. So mass, we write it m, and then volume L cube, so that it will become m L to the power minus 3. Right? So mass is m and L to the power minus 3. So the second slide of dimensions of derived physical quantity is clear. Any doubts in this? No? Chalo. So now let's increase one more level. So the angular velocity. So what does it mean by angular velocity? So this might be very new to you. So V is equals to R omega is the formula. V, the linear velocity, is equals to R into the angular velocity. Omega is the angular velocity. V is the linear velocity. Okay. So this we come across in the second chapter itself, NLM. So there I'll explain in detail. So now, so from here, shall I write omega is equals to V by R? Omega is the angular velocity. So which is equals to linear velocity by R. R is the radius. So which is equals to, so I can write the formula V by R. V by R. So velocity formula you already know. So what is the velocity formula we learned? So L t to the power minus 1, speed or velocity, L t to the power minus 1 by, so R is nothing but the distance. R is nothing but the distance. So which is L, right? So radius is nothing but the distance we measure. So which is nothing but L. So L cancel, t to the power minus 1. T to the power minus 1. So and then frequency. So frequency is equals to F. So the frequency formula is 1 by time period. So 1 by time period means again t to the power minus 1. So F is equals to 1 by t. So where the dimensional formula is t to the power minus 1. And angular frequency, which we denote it with omega. So the angular frequency will have the same dimensions, which is t to the power minus 1. So clear these three terms, the angular velocity, frequency, angular frequency. So they all will have the same formulas. So now the angular momentum is again the new term to you. So which is equals to mvr sin theta is a formula. Okay, na? mvr sin theta is a formula. So one thing you should remember while writing the dimensional formula, that is, so the sin theta trigonometric ratio, cos theta trigonometric ratio, tan theta. So such trigonometric ratios do not have any dimensions. You can consider them as a dimensionless quantities. So the trigonometric ratios. And wherever you see the numerical, just 2, pi, so those are all the constants. So they do not have any physical dimensions. Okay, so you can just ignore them. So in this formula also, you can ignore the sin theta. So and m is a mass, v is a velocity, r is a radius, which is nothing but distance. So mass, you know that m, and then so velocity, you know that L t to the power minus 1. Velocity is nothing but distance by time, right? So and then L is again, R is again the distance. So from here we get m L square t to the power minus 1. So m L square t to the power minus 1. So the angular momentum is m L square t to the power minus 1. Clear? So similarly, the angular acceleration, so which is denoted as angular acceleration alpha. So which is change in angular velocity by change in time. The change in angular velocity by change in time. So what is angular velocity dimension? T to the power minus 1. Angular velocity dimension is t to the power minus 1. We already wrote this, omega is equals to v by r. V is L t to the power minus 1 by, so r is L. L cancel, t to the power minus 1 we got. So by time is t. So if it goes up, so it becomes t to the power minus 2. T to the power minus 2. Clear? And moment of inertia. So this is also a new term. So whose formula is mr square. Just remember the formulas. Once we complete the chapters, so then you'll understand how these formulas has arrived. Okay. Chalo. So mr square. So in place of mass, you can simply write m, and in r square, so it's nothing but L square. So this is a dimensional formula, m L square, right? So the third slide of the dimensions of derived physical quantity is clear. So 20 we have derived till now. So in these 20, almost 15 above, you already know these formulas. So some 4 or 5 formulas which are new, I already told, then you should remember, that's it. Okay, chalo, let's move further. So now the coefficient of restitution, so this will come across in collision chapter. So the coefficient of restitution, which is denoted by E, so which is, so the relative velocity of separation by the relative velocity of approach. So in the numerator also it's velocity, in the denominator also it's velocity. So these units and these units gets cancelled, so that the coefficient of restitution is a dimensionless quantity. Remember this one. This is a dimensionless quantity. Coefficient of restitution is a dimensionless quantity. Okay, chalo, next. So stress. So stress you already know, right? What's the stress formula? So the force upon area, right? So the force upon area. So you know the dimensions of force. What are the dimensions of force? M L T to the power minus 2. So and then area. Area means L square, right? So this comes out to be M. If it goes up, L to the power minus 2 and L to the power 1, which is L to the power minus 1 and T to the power minus 2. So these are the dimensions of stress. Stress is nothing but force upon area. Clear? And then, so strain is nothing but, so the change in length by original length. The strain formula is change in length by original length. So above length and denominator also length. So length gets cancelled. So it's a dimensionless quantity again. It's a dimensionless quantity. Clear this part? Chalo, next. So the Young's modulus of elasticity. So what is the Young's modulus of elasticity? So any modulus of elasticity is nothing but stress by strain. Any modulus of elasticity, so it's going to be stress by strain. So you know that stress has no dimensions. So therefore, whatever the dimensions are there for the stress, the same dimensions will be there for the Young's modulus of elasticity. So which is nothing but, what is the stress dimensions? M L to the power minus 1, T to the power minus 2. M L to the power minus 1, T to the power minus 2. So just understand the concepts. Okay. Chalo. So the surface tension. So the force per unit length. So you know the dimensions of force M L T to the power minus 2 by length is L. Right. So now L gets cancelled. So we have simply M T to the power minus 2 is the dimension of surface tension. Done. So and then, so surface heat capacity. So heat capacity. So this formula you should remember, guys. So the heat capacity Q is equals to MC delta T. MC delta T. So in this, so C is a specific heat capacity or surface heat capacity, which is Q by M delta T. Q by M delta T. So this you should write it as C is equals to Q by M delta T. So where Q is a heat energy. Remember, Q is a heat energy. So energy formula you know, right? Q is nothing but a form of energy. Heat is a form of energy. So therefore, heat dimensional formula you can write M L square T to the power minus 2. That's a energy formula by. So this is mass M, and then delta T, which is nothing but K, change in temperature K. So then M cancel, which is L square T to the power minus 2 K to the power minus 1. L square T to the power minus 2 K to the power minus 1. Understood this formula? How this has arrived? C is equals to Q by M delta T. Q is nothing but energy. Energy, in place of energy we can write M L square T to the power minus 2 by. So in place of mass, dimension is M. So and delta T Kelvin. So therefore M cancel, L square T to the power minus 2 K to the power minus 1. Clear? Any doubts here? Chalo. So now, so the wavelength is nothing but it's a length. It's measured in meters. So the wavelength is nothing but the length. So whose dimensions will be simply L. Wavelength is measured in meters, centimeters, like that, or angstroms. So which is nothing but a quantity related to the length. So and then charge you already know. So what is charge? See, here I'll write. So Q is a heat. Okay. So whereas charge is also denoted by Q. You know that. So I is equals to, the current I is equals to Q by T. So from here Q is equals to I into T. So where Q is a charge, this small q is a charge I am writing here. So where I is the current, T is the time. So here I can write the formula I into T. I dimensional formula is A, and then T. So clear till 28th. Done. Let's move further. So now the electric potential. So these are all most of the terms related to the second year concepts. Okay, so these terms, some of the terms you already learned in the grade 10th level. So but most of the terms you don't know the formulas. So just remember the formulas, whatever I am going to discuss now. So the electric potential. So what is the electric potential definition that you know in the grade 10th? So the work done in bringing a charge, right? So the work done in bringing a charge, which is denoted by V, which is equals to the work done in bringing a charge, where Q is a charge here, or else let me use the small q to avoid the confusion. So work done, dimensions you already know. Work done is ml square t to the power minus 2 by, so what is charge dimensions? Charge dimensions are I into t, current into time. So which is nothing, current is A, so time is t. So now let's write this one, m L square, if this t goes up, so minus 1 will add. So t to the power minus 3 and a to the power minus 1. So everyone clear with the potential, electric potential units, dimensions? Just the basic formula, work done per charge, right? Work done in bringing the charge. So work done is m L square t to the power minus 2 by charge is current into time, I into t, which is a into t. Current is a and t. So just send these two terms to the numerator part. Done? Chalo. So now the electrical resistance, you can write the resistance formula from Ohm's law, V is equals to IR, right? You know that from Ohm's law, V is equals to IR. So and from there, the resistance R is equals to V by I, shall I write? So the same thing I am writing. So V by I, V by I. So the potential, V is nothing but the electric potential. So just now we wrote, so which is m L square t to the power minus 3, a to the power minus 1 by, so the current I, which is nothing but A. So if I send this upside, so m L square t to the power minus 3. So if this A goes upside, a to the power minus 2. So this is a dimensional formula of the electrical resistance. Clear? Chal. Next. See, this is one method. Sir, if I don't know this electric potential formula, then how can I derive the electrical resistance dimensional formula? So then again a question, right? So you can use the another way. What's that, sir? So you can use, you know that in the grade 10th level, the Joule's law of heating. So the heat is equals to heat dissipated, H is equals to I square RT. So from there, the resistance R is equals to H by I square T. So here you know the dimensions of every term. H is the heat, I is the current, T is the time. So from now, from this, you just derive the resistance dimensional formula. So take that as a homework. You should get the same thing. So take that as a homework, guys. So I should see it in the comments. Sir, I got the same answer as this. So if you are not getting, you are doing something wrong. Okay, so just do that on your own. So then electrical capacitance. So the capacitance formula C is equals to Q by V. So where Q is a charge, V is a potential. So here C is equals to, we can write Q by V. So we know that Q is equals to, Q is a charge, which is A into T. And potential also we know that, what is the potential? M L square T to the power minus 3, A to the power minus 1. So from here, I can write if M goes up, it is M to the power minus 1. If L square goes up, L to the power minus 2. And then T to the power minus 3 is there. If it goes up, T to the power 4. Already 1 is there, na? So that's why. So A to the power minus 1, if it goes up, A to the power 2. Because already 1A is there in the numerator. So this is a dimensional formula. Right? Sorry if I don't know what is the potential formula. Again, we have another shortcut. So that is, so the potential energy, sorry, the capacitance is the U energy is equals to Q square by 2C. Q square by 2C. So then C is equals to Q square. This is a energy stored in a capacitor formula. U is equals to Q square by 2C. So which will come across in grade 12th. So just I am telling you the different methods because you learn all these formulas in the upcoming classes. Okay. So combinedly, this all the chapters combinedly, the formulas whatever that are there. So those dimensions I am writing it in the units and dimensions. That's our first chapter actually. Okay. So U is equals, C is equals to what will be the C? So Q square by 2C, 2U, sir. Q square by 2U. So you just do this as a homework again. You should get the same dimensional formula as of this. So you know what is Q, and you know U is the energy here. You use the energy formula, and this Q is the charge, guys. Okay, so don't get confused. So Q is the charge and U is the energy stored in a capacitor. So energy, whatever the energy that is, you can just use the energy dimensional formula here. Done that part. Chal. So let's move further. So then we have the electric field. So the force experienced by a charge which is placed near the charge. So that is called the electric field. So which is force upon the charge Q. So you know the force units. What are the force units? mLT to the power minus 2 by, so the charge, so Q is equals to IT. IT means A into T, right? So then simply M here send L, so that's it. So and T if you send up, T to the power minus 3, so then A to the power minus 1, right? Chalo, next. So and then we have electric flux, which is phi E. So the formula for this is E dot A, which we write it as EA cos theta. So the electric flux is E dot A, which is EA cos theta. So now E is the electric field, A is the area. So where cos theta is the trigonometric term, which is a dimensionless quantity. So here electric field, you already know. So what's that? mLT to the power minus 3, A to the power minus 1. And area A, so length square. So which is nothing but L square. So whose dimensional formula will become M. So here L square into L to the power 3, M L to the power 3, so T to the power minus 3, so into A to the power minus 1. So this is the dimensional formula for electric flux. And then, so the temperature gradient, so the change in temperature per length. So previously only I discussed, so the temperature gradient in the starting. So where did I write that? So here. So somewhere around here I wrote that. Where is that? So here, see here, the temperature gradient, the change in temperature per length. So the same thing I am writing here now. So what is the change in temperature? So Kelvin per length L. So which will become KL to the power minus 1. Done. So and radius of gyration is the length. So this is the quantity which is measured in length. It's a quantity related to the length. So that's why simply write L. So that we come across in gravitation chapter in first year only. Okay, so there I'll discuss in detail. Done. Clear? Chal. Next. So now, so there are three important terms, so whose dimensions you should remember for sure. So that is coefficient of viscosity, so universal gravitational constant and Planck's constant. So these are the mostly commonly asked terms. So whenever a question appears related to units and dimensions, so most of the times these terms, one of these terms will be appeared in the exam. Okay, so that's why. So how to remember these three terms? So for that I am going to tell you the trick. So one is the formula method. So here I am going to tell one simple trick. Just remember their units. So from units you can write the formula. So here first let me write the formula, then I'll tell you the trick to remember the dimensions. So this formula, the viscous force is equals to minus neta A into, so the dV by dz or delta V by delta Z also we can write. So where this is a viscous force. So this is a coefficient of viscosity neta, and this term is a area, and this is a velocity term, and this is a distance term. Okay, so you know the dimensions of all these. You know the dimensions of everything: force, area, velocity, distance. So you just substitute all the dimensions and get the dimensions of neta. So that's one method. So you take that as a homework, but I'll use the very simple method, that is the units of coefficient of viscosity. So the units of coefficient of viscosity are kg per meter second. Kg per meter second. That's it. So now I can easily write the dimensions here. So what will be the dimensions? So kg, which is related to mass, so therefore m, and then so meter, so which is related to length, and second, time, so which will become m l to the power minus 1 t to the power minus 1, m l to the power minus 1 t to the power minus 1. That's it. So you do by this method. So you take this as a homework. By formula method, you should get the same. Okay, na? So instead of remembering this formula, you can just remember the units. Done? Chalo. So the universal gravitational constant, this you already learned in the grade 9th formula. So what's that? F is equals to G m1 m2 by r square, where G is the universal gravitational constant. So what's the formula that you can write? F r square. So this m, let's consider them as identical masses. So m square. So now what will be the units? Tell me. So here force units you know, r units you know, r is the distance. So m is a mass units you know. So you can get the formula, the dimensional formula. So take this as the homework. Take this as a homework. So instead of this, what I'll do is, so by units method I'll write. So what are the units for this? So the units will be force is measured in Newton. So r square, distance square, meter square, by so mass square, which is kg square. So then simply I can write, so Newton force is nothing but ml t to the power minus 2. So then meter square, what is meter square? So meter square means L square, kg square, which is m square. So then I will get this, if it goes up, m to the power minus 1. So L into L square, L to the power 3, and then t to the power minus 2. That's it. These are the dimensions of the universal gravitational constant. So I'm telling you the simplest method, or else you can use the same formula method also. Done? Clear, guys? Chal. So next. So the third one that you should remember is the Planck's constant, which we'll get it in the second year. So the Planck's constant, so the E is equals to, the formula is hf. So where h is called the Planck's constant. So which is equals to energy. So E is the energy, whereas f is the frequency. So we know the dimensions of frequency and we know the dimensions of energy. So this, by this method you can find the dimensions. So you just take this as a homework. So I am not going to use that. So what I'll do is, so to remember easily, I'll just remember the units of this. So what's that? Units joule second. I'm using the units joule second. So the joule second, joule is nothing but, joule is a work, right? So which is m L square t to the power minus 2, and then second is time. So then I can write the dimensions as m L square t to the power minus 1, m L square t to the power minus 1. Clear this part, everyone? Understood? Simple thing. So these three you should do, guys. Okay, na? So just take this as the formula method as homework. So but unit method, through that I got the dimensional formula like this. Done? Clear? Chalo. So let's move further. So again we have something. So the Boltzmann constants, these are also the frequently asked terms. So here, so the Boltzmann constant, the formula here, the kinetic energy of a gas, which is equals to 3/2 kT. So where this small k is a Boltzmann constant. Okay, na? So this 3/2 will not have any dimensions. So from here I can write the Boltzmann constant k is equals to the kinetic energy Ke by, so this is temperature T. Okay, na? So therefore this is the energy, and then this is the temperature. This is the temperature. So now can you find the dimensions? So energy dimensions we already know. So energy is nothing but m L square t to the power minus 2. So and the temperature Kelvin. So which is equals to m L square t to the power minus 2 k to the power minus 1. M L square t to the power minus 2 k to the power minus 1. Done? Clear? Chalo. So now let's go for the molar specific heat capacity. So here for molar specific heat capacity you should remember the formula. So which is NC delta T. So which is NC delta T. So where, So this N is a molar specific, sorry, C is a molar specific heat capacity. So Q is equals, C is equals to Q by N delta T. Okay now. So what is this Q? So this Q is a energy here. So what's the energy formula that we can write? M L square T to the power minus 2. So by, so this N is the number of moles. For number of moles we use MOL, right? So change in temperature, Kelvin. So if you send these two up, so M L square T to the power minus 2, K to the power minus 1 and the mole inverse. So these are the dimensions of molar specific heat capacity. So and the next one we have the specific density. So this is nothing but the density of substance by the density of water. The specific density is nothing but density of a substance by density of water. So numerator is also density, denominator is also density. So as two quantities are densities, so their units gets cancelled. So this specific density is a dimensionless quantity. It's a pure number. It's a dimensionless quantity. Remember this. Okay now. So previously we have got dimensionless quantities. What are the dimensionless quantity? Strain is a dimensionless quantity. And then specific density is a dimensionless quantity. Coefficient of restitution is also dimensionless quantity. And one more dimensionless quantity, just let me write here. So one more dimensionless quantity, I'll write it down here. See here. So one more dimensionless quantity, that is refractive index. So you know the refractive index in grade 10th, right? So the refractive index mu is equals to C by V. So speed of light in vacuum by speed of light in medium. So V is the speed of light in medium. So where C is the speed of light in vacuum. So both are speeds. So their units will get cancelled. So that's why the refractive index is also a dimensionless physical quantity. This is also the dimensionless physical quantities. Dimensionless physical quantity. Clear? Understood everyone? Any doubt related to this? Terms clear? Chal. So next, let's move further. So there are two supplementary physical quantities we have. What are those two supplementary physical quantities? One is plane angle, the other one is a solid angle. So these two supplementary physical quantities, they'll have the units. So the unit of the plane angle is radian, whereas the unit of the solid angle is steradian. So they have units but no dimensions. So two supplementary physical quantities have units but no dimensions. Okay now. So this statement can be given as a assertion reasoning question type, or which of the following can be true. So like that question can be framed on this. So a physical quantity can have units, but it may or may not have the dimensions. Okay, it may have or it may not. Okay, so but if any physical quantity has a unit, it must have dimensions. So if any physical quantity has dimensions, it must have units. Okay, so any physical quantity which has dimensions, it must have the units. But all the physical quantities which have units may or may not have the dimensions. Clear this part? Understood? Chalo. So remember that statement, guys. Chalo. So now let's take some questions. One by one, we'll take the questions. So whenever the question appears on the screen, just pause the video and try it on your own, guys. That's the best way to learn while studying. Okay. So if you don't get, so then go for the solution. But first try it on your own, because so that develops the thinking skills. Okay now. So whenever you see the question, so you think in different ways. Okay. So through that you can adapt the learning. Like, so how I am approaching this question. So where I am doing the mistake. So how should I approach it? So those things you learn it. Okay. So you might you may follow the long procedure, right? So I might deal with the shortcut. So this difference you'll understand once you started doing it on your own. Okay. Chalo. So let's solve the first question, guys. See here what's the question says. The damping force on an oscillator is directly proportional to the velocity. The units of the constant of proportionality are. So what they are saying, the damping force, some force, whatever the force that is, let it be F. So it's directly proportional to the velocity. So F is directly proportional to velocity. So now I am taking out the proportional symbol and put the proportional constant as K. So F is equals to kV. So now I need the dimensions of the proportional constant. So K is equals to what will happen? Force upon velocity. We know the dimensions of force. What are the dimensions of force? mLt to the power minus 2, right? So by the velocity dimensions you already know. So the Lt to the power minus 1. Right? So V is Lt to the power minus 1. So then here L cancel. So M, if this goes up, T to the power 1. So M T to the power minus 1 it becomes. So M T to the power minus 1. So what is that? M T to the power minus 1 means M is mass kg. So time is second inverse. So kg second inverse. Option C is a, guys. How many of you did correct? Just mention it in the comment just before I solve. How many of you solved on your own? Not after I am solving. Right? Chalo, guys. Next, let's move further. Next question. So here, the unit of permittivity of free space is. So the unit of permittivity of the free space. So here, this you can learn from the second year, the first chapter, electric charges and fields. So where the force between the two charges will be given by 1 by 4 pi epsilon naught q1 q2 by r square. So where this epsilon naught is called the permittivity of free space. This epsilon naught is called the permittivity of the free space. So now, how do we get the formula for this? However, here 1 by 4 pi is the constant. Just you can take that off. So just I am writing it as epsilon naught is equals to, so which is send this to this side and force to this side. So Q, let's take these identical charges, Q square by F into R square. Shall I write like this? Q, consider them as identical charges. Then Q into Q will become Q square. So epsilon naught I sent it to this side, F I sent it to this side. So then R square. So here Q is nothing but what are the units of the Q? So Coulomb. So I can write in place of Coulomb Q. So the Coulomb square by force is denoted by Newton. And then so R is the distance. R we can write meter. So the unit. So just proceed along as per the options. So R square, which is square. So check this option. Where do we have this? So Coulomb square, no, not this one. Newton meter square, no. Coulomb square per Newton meter square. Yes. Newton. See, this is Newton meter whole square. For Newton also here square is there. So don't select this option. So just check the options properly once you solve the question. Done, guys? Chalo. Let's move further. Next question. So the dimensions of mu naught epsilon naught power minus 1 by 2. See, so to solve such kind of questions, so we can use the formulas. See, in electromagnetic waves, we get this formula. C is equals to 1 by root of mu naught into epsilon naught, where C is the speed of light, right? So then C is equals to, shall I write what is this one? 1 by mu naught epsilon naught whole to the power 1 by 2. So then C is equals to, so if I send it to upside, mu naught epsilon naught whole to the power minus 1 by 2, right? So here I can write like, so these units, they are asking the units of the same, right? So these units are equals to the units of C. What is C? Speed of light. This C is the speed of light. So the speed of light will have the units of meter per second. This will have the units of meter per second. So whose dimensional formula will be meter L. So second T to the power minus 1. So because it's in the denominator, right? So that's why L T to the power minus 1. So this is the simplest way by using the formula. So otherwise you can derive the formula for mu naught. You can derive the formula for epsilon naught. So then substitute those two, do minus 1 by 2. So that's the longest procedure. So you can simply use this formula. Right? Understood? Chalo. Let's move further. So the next question, see here, the dimensions of epsilon naught E square, where E naught is the permittivity of free space and E is the electric field. So you know the epsilon and you know the E square. So these two formulas you just write down. So you guys take this as a homework, because just now we did. So epsilon naught units, how can we derive? So the epsilon naught units you can derive from the force is equals to 1 by 4 pi epsilon naught Q square by R square. So from here you can write like epsilon naught is equals to, just take this off 4 pi, however it do not have any dimensions. So Q square by, so force into R square. So Q is the charge, where you can write AT whole square, right? So charge is nothing but current into time. So which is AT whole square by, so force we already know, ML T to the power minus 2 and R square L square. From there you get the epsilon naught units, right? And then next we have the electric field. E is the electric field, they said. Electric field units, how can you write? Force upon charge, force upon charge. So which is nothing but force is ML T to the power minus 2. So the charge is current into time. So which is I into T. So which is nothing but you can write AT simply. So AT, right? So here, so you just E we have and we have epsilon naught. So now you have to find the epsilon naught E square. So can you guys do this as a homework and comment your answer? Just I'm giving this as a homework, because everything you know, just you have to substitute and get the answer. Okay, so you do that and comment your answer. So for the question, what's the option A, B, C or D? So let's consider this as a homework 1. Okay, so while mentioning in the comments, so write what's the answer for homework 1. Okay, chal. Next, so let's take the next question. Which two of the following five physical quantities parameters have the same dimensions? So the energy density, energy per unit volume. So the first one, let's take, so the energy per volume. Let's derive for all. So the energy per volume. So which is equals to, what is energy? ML square T to the power minus 2. Just learn first. So by volume, L cube. So we get, so if I send this to upside, L to the power minus 3, L to the power 2, which is L to the power minus 1, T to the power minus 2. So just let it be. This is the energy density. So the second one, refractive index, mu is equals to C by V, which is a dimensionless quantity. Which is a dimensionless quantity, right? And then, so we have something called dielectric constant. So where, so the dielectric constant, new capacitance C dash is equals to K into the original capacitance C naught. Okay, na? This formula you learn it in the capacitors, just understand the process. So here K is the dielectric constant. K is equals to C dash by C naught. So C dash is the capacitance, C naught is also the capacitance. Capacitance by capacitance. Again, this is the dimensionless quantity. This is also the dimensionless quantity, right? So that means 2 and 3. Check the options. Is there any 2 and 3 option? There is no 2 and 3. So we have to proceed further. So then check the fourth one, the Young's modulus. So the Young's modulus Y is equals to, we can simply write stress by strain. So stress is a strain is a dimensionless quantity. So which is equals to simply stress. So stress is equals to what? Force upon area. So what is force upon area? Force is ML square, ML T to the power minus 2. By area, it's L square. So then if it goes up, it becomes M L to the power minus 1. So T to the power minus 2. So it's matching with the first one. M L to the power minus 1, T to the power minus 2. So simply you can go for the 1 and 4. So 1 and 4. 1 and 4. Option A is the correct answer. Clear? Understood, guys? Clear? Chal, next. So let's move further. So the next question. The dimensions of resistance in an electric circuit in terms of dimensions of mass M, length L and time t and current I would be. So resistance, the easiest way to derive the resistance dimensions are, so use the Joule's law of heating. So H is equals to I square RT, right? So from there the resistance is equals to H by I square T, right? So H by I square T. So where I is the current, so H is the heat, which is nothing but energy. So in place of energy you can write m L square T to the power minus 2 by, so current, let it be current itself. So they mentioned it as current, let it be I square itself. So then what they said, so then T, so T to the power, time is T only. So then send these two upside, so m L square, so if it goes up, T to the power minus 3 and I to the power minus 2. So m L square T to the power minus 3, m L square T to the power minus 3, not this one, not this one, m L square T to the power minus 3, I to the power minus 2. So here they took 2 t's, it's I. Take this as I, guys. So I to the power minus 2. So just printing mistake. So this is I to the power minus 1 here. So not I to the power minus 1. It's I to the power minus 2. So just correct that one. Done? Chalo, next. So let's move further. What's the question says here? The ratio of the dimensions of Planck's constant and that of the moment of inertia as the dimensions of. First derive the Planck's constant. So H is the Planck's constant. What's the simplest way I told you to derive the dimensions of Planck's constant? Just remember its units, joule second. So joule means energy, so which is m L square T to the power minus 2. So second is time t, so which becomes m L square T to the power minus 1. This is the H, Planck's constant. And the moment of inertia, I is equals to m R square. So what is m dimension? M. So R L square. So moment of inertia is m L square. Now what they are asking? The ratio of the dimensions of Planck's constant to that of the moment of inertia. So H by I dimensions they are asking, ratio. So H is m L square T to the power minus 1 by here m L square. So m L square cancel. So which is nothing but T to the power minus 1. So 1 by time. So 1 by time is nothing but whose frequency units are 1 by time. Frequency dimensions. Frequency is equals to, we know that 1 by time period, whose dimensions will be T to the power minus 1. Right? So the Planck's constant ratio to that of the moment of inertia will have the dimensions equals to frequency. So you guys are understanding, right, how to solve the questions and how to do the dimensional analysis. Here formulas plays a crucial role. Okay, so as the classes progress and we cover the chapters, you understand the formulas. Okay, but as of now, you just have to by heart the formulas. So just you are studying the first chapter, you should by heart these things. Okay, once we cover those chapters, automatically you learn. Done? Chalo, next. So let's move further. So the dimensions of universal gravitational constant, either you do it through the units or you go through the formula, your wish. F is equals to G m1 m2 by r square. So here I can write, let's consider these two masses are identical. So then G will be equals to F square by m square. So force units are m L T to the power minus 2 and then R is L square. So mass is m square. So if you substitute here m to the power minus 1, L to the power 3, T to the power minus 2, m to the power minus 1, m to the power minus 1, L to the power 3, T to the power minus 2. Option A is the correct one. Clear? Chalo. So let's move further. So we have one more question, see here. So the dimensions of the Planck's constant equal to, first Planck's constant units are, what are the Planck's constants units? H. So it has the units as joule second. Write the dimensional formula for that. So joule is m L square T to the power minus 2 and second is time. So which is nothing but, so the Planck's constant as m L square T to the power minus 1, m L square T to the power minus 1. So now check which one has the same dimensions as of the Planck's constant. So energy means m L square T to the power minus 2. So this one is not same, cancel that. momentum. Momentum is nothing but mass into velocity. Mass is m, velocity is distance per time. So lt to the power minus 1. So mlt to the power minus 1, no. So the angular momentum. So what's the angular momentum formula? mvr. So what is m? M dimensional formula. V lt to the power minus 1, r l. So which is nothing but which is equals to m l square t to the power minus 1. So see here, m l square t to the power minus 1 and angular momentum also m l square t to the power minus 1. So the same thing. So if you want to check the power also. Power is nothing but work done by time. So work done is m l square t to the power minus 2 by time is t. So here m l square t to the power minus 3. M l square t to the power minus 3. So which is again not matching with the Planck's constant. Clear? Done, guys? Sure. Let's move further. So which pair do not have equal dimensions? Which pair do not have equal dimensions? We know that energy and torque have the equal dimensions. We studied that energy has m l square t to the power minus 2. So these are for the energy. So what about for torque? So torque also will have the same. Torque is equals to force into perpendicular distance. Force into the perpendicular distance. So force is nothing but m l t to the power minus 2. Perpendicular distance is l. So again we get the m l square t to the power minus 2. So that means energy and torque have the same dimensions. So they said which do not have. So then force and impulse. Force has a m l t to the power minus 1. Force has m l t to the power minus 1. This is for the force. So then what about for the impulse? Impulse is equals to force into time. Obvious force is there. Force into time is there. Here force is this one. Force into time means time is adding extra. Compulsory these two will not have the same dimensions. So what about angular momentum and Planck constant? Just now we discussed. So the angular momentum and Planck constant will have the same dimensions, right? So this also true. So what about elastic modulus and pressure? So what does it mean by elastic modulus? Modulus is nothing but so stress by strain. Stress by strain. As strain has no dimensions, which is equals to simply strain. Strain is nothing but force per unit area. So pressure is also force per unit area. Same thing. So force per unit area, force per unit area. So these two also will have the same dimensions. Clear? Understanding? Right. So next. So the dimension formula of magnetic flux. So here the magnetic flux of phi b is given as BA cos theta. So where B is the magnetic field, A is the area, cos theta, however, it's the trigonometrical term, so need not to go for the dimensions of that. So now area we know, so from where do we get the magnetic field? So here you use this formula. So for the magnetic field, the distance between two current parallel carrying wires. So this question you should take it as a homework. So I'll give you the hint. So the force between the two parallel current carrying wires is given by, so mu naught by 4 pi into 2 I1 I2 by, so the distance between them is d square. So from here, however, 4 pi is constant, 2 is constant. So I1 I2 consider them as identical currents. I1 I2 consider them as identical currents. So now from here you have to find the mu naught formula. So mu naught is equals to, sorry, we need B kada. So my bad guys, very sorry. I thought mu naught, magnetic permeability. So B, to get the B, so just use this formula. F is equals to Bill sin theta. F is equals to Bill sin theta. So where B is the magnetic field, I is the current, L is the length. So sin theta. So this is a force on a current carrying conductor. So where we need B gada. So B is equals to F by I into L. So you know the force dimensions, which is M L T to the power minus 2. So you know the current dimensions A and length L. So here L cancel. So M T to the power minus 2, A to the power minus 1. A to the power minus 1. So we have got B, which is M T to the power minus 2, A to the power minus 1. and then area, this is area. Area is L square. So however, cos theta do not have any dimensions. M L square t to the power minus 2 a to the power minus 1 final. So M L square t to the power minus 2 a to the power minus 1. Option C is the correct one. Understood, guys? Chalo. Next. So the dimensions of impulse are equal to that of. First, what are the dimensions of impulse? Impulse is equals to the change in momentum, right? So you can remember like this, or you can just remember the formula for impulse, which is force into time. So which is change in momentum is nothing but F into, see, already direct question is there. Direct option is there. Need not to go for anything. So I am saying that impulse is equals to change in momentum. So whatever the dimensions of impulse are there, will be there for the same linear momentum. So remaining all the terms dimensions also we know. So this is pressure, force per area. Force you already know, ml t to the power minus 2, and angular momentum L is equals to mvr. From there you can derive that. Clear? Done? Chal. So next, so which of the following dimensions will be same as that of the time? So this question, see here, will be having inductive time constant and capacitive time constant. So the inductive time constant, which is given as L by R. So the inductive time constant T is given as L by R. So this you learn it in the electromagnetic induction chapter. So which of the following will have same as that of the time? Okay, so inductive time constant. So with T is equals to L by R. So that L by R will be same dimensions as of the time. So just remember this one. This we'll discuss in detail in the EMI chapter. Okay. So whereas one more term also will be there, that is capacitive time constant. So that is RC. So we do not have any. So RC also will have the same units as that of the time. Okay, remember these two. L by R will have the same units as of the time, and then RC also will have the same units as of the time. So these two you learn it in the EMI chapter of second year. Okay, plus 2 low, 12th class. Done? Next. So which of the following is a dimensional constant? So which of the following is a dimensional constant? Following is a dimensional constant or not dimensional constant? Which of the following is a dimensional constant? See here. So we have the Poisson ratio, refractive index, and relative density. So the relative density is a dimensionless quantity. So this is a dimensionless quantity. So relative density means density of one substance with respect to the another. So then units will be cancelled. So there will be no dimensions. So gravitational constant has the dimensions. So gravitational constant has the dimensional formula. So what's the dimension formula for this? So we can write F is equals to G m square by R square. From here you can write G formula as F R square by m square. We already derived the formula. So this will have the dimensions. So as I said earlier, refractive index will have no dimensions. So this is also the dimensionless quantity. This is also the dimensionless quantity. So the Poisson's ratio. So the Poisson's ratio is also it's a strain by strain. So which is nothing but again the dimensionless quantity. So it's also the dimensionless quantity. So remember this, the dimensionless quantities. So write all of them at one place. So in this they are asking which is the dimensional constant. Only gravitational constant. Remaining all three, they do not have the dimensions. They are pure numbers. They are dimensionless quantities. Clear? Understood? Chal. Next. So the dimensions of RC, as I told you previously, so RC is a capacitive time constant. RC will have the same units as of the time. Okay, na? R by L, L by R will have the same units of the time, and then RC will also have the same units as of the time. Okay, chal. So the dimensional formula of permeability of free space. So the permeability of free space, you just take this question as a homework. I'll tell you the procedure. So what's the procedure? So to get this formula, I'm using the formula, the force between two current carrying wires. Let the distance between these D. So in this, current I1 is flowing, current I2 is flowing in this. So then the force between these two wires is given by mu naught by 4 pi into 2 I1 I2 by the distance square. So from here, can you get the formula for mu naught? From here, can you get the formula for mu naught? So the mu naught is equals to F into D square. However, 4 pi do not have any dimensions. 2 do not have any dimensions. Let's consider the current as identical. Then I square. So force units you know, the distance units you know, current units you know. So everything you know now. So just get the formula. Okay na? So put your option. Consider this as a homework 2. Done? Clear? Chalo. So next. So the dimensional formula of self-inductance. So the self-inductance E is equals to minus L into di by dt. So this L is a self-inductance formula. So where this E is a EMF. So EMF means voltage only. So what's a voltage formula? V, in place of this, we can write the work done in bringing the charge. And then, so let's take out the minus. So L we required. So the current I, so the time T, right? So you know the dimensions of everything now. So work done is mL square T to the power minus 2. Just you have to remember this formula. E is equals to minus L into di by dt. Okay. So E is nothing but the potential, EMF. So which is work done in bringing the charge. So what is charge dimension? So this is fine. So the charge is equals to current into time. So which is A T. So then here in place of L, we have to find its dimensions. L is not the length here. L is a coefficient of self-inductance. This is a self-inductance. So we have to find that units. So into A by T. Into A by T. So here A cancel. So you just send A to this side. So then units will be m L square T to the power minus 2. So here A to the power 2. So if you send it to upside, m L square T to the power minus 2 A to the power minus 2. M L square T to the power minus 2 A to the power minus 2. M L square T to the power minus 1. M L square T to the power minus 2 A to the power minus 2. Option C is the correct one. Understood? Chal. So next. So according to Newton, the viscous force acting between the liquid layers of area A and viscous velocity gradient delta V by delta Z is given by viscous force is equals to minus neta A delta V by delta Z, where neta is a constant called coefficient of viscosity. So the dimensions of coefficient of viscosity, no need to use the formula. So just I told you, right, units of coefficient of viscosity. Just remember this one, units of neta. What are the units? kg per meter second. Kg per meter second. So kg means m, mass. So meter, L, second, time. So that m L to the power minus 1 T to the power minus 1. That's it. M L to the power minus 1 T to the power minus 1. Option D. Done? Chalo, simple question. So whatever we have learned in today's session is just about the dimensions. So almost above 50 physical quantities dimensions I wrote in the class itself, and we solved various numericals as well. So what you guys have to do is just revise the things. So there are main physical quantities which we have. So this is represented for mass, and then this is represented for the length and for time t. So these are mainly we used, right? Okay, and revise all the formulae for all the concepts, for all the dimensions to get. We should remember the formula. So first you learn the formula. Okay, so there are some new formulas are there in the class I gave. So those formulas will come across in the future upcoming classes and upcoming chapters. Okay, so you don't just worry about that. You just learn the process, how we write the dimensional formula if we know the formula of anything. Okay, na? So that we learned in today's class. So don't worry about, Sara, I did not learn this formula, I don't know this formula, that formula. Don't worry about that. Okay, na? So because you are just entered the 11th class, and these are all the things which will get it in upcoming chapters. Okay, so just revise the complete class, basic formulas. So what you have to do? So force, work, energy, force. So and then these compulsory, these you should remember, mLT to the power minus 2 for force, and then for work and energy it's mL square T to the power minus 2. So you also list down what are all the dimensionless physical quantities. So what are all the dimensionless physical quantities? So whatever we learned in today's session, so you just list them down. And which physical quantities have the same dimensions? Which physical quantities have the same dimensions? So like we learned that the dimensions of Planck's constant and angular momentum are equal. So like that we learned in the today's class, right? So some of them you just list them down, and dimensionless physical quantities you list them down. So on basic things you just list them down. So just write it as a short notes. Okay, so that's it, guys. So this is my first class of units and dimensions. So in the next class we'll see the principle of homogeneity, and if we don't know the formula, how do we derive the formula using the dimensions? So that we'll learn it in the next class. And we'll also learn the significant figures, error analysis, all these we'll do it in the second thing. Chalo, so we'll meet in the next session, guys. So till then, keep studying. All the very best. Bye. Take care.